Welcome back to the deep dive. Today we are taking on, well, maybe the most dominant yet most mysterious force in the entire universe.
It's a big one.
A huge one. A phenomenon that is actively shaping our cosmic destiny. Yet it remains utterly invisible and, frustratingly, completely unexplained. Dark energy.
Right?
So if you're looking for a shortcut to understanding what is probably the single greatest puzzle in modern science, you are absolutely in the right place because the implications of this stuff they're truly massive and, I think, truly philosophical.
They are quite literally universal.
Yeah.
I mean, if we accept the current standard model of cosmology, the lambda CDM model, dark energy isn't some, negligible add-on.
No.
It is the universe, or at least the bulk of its energy budget. It makes up a staggering 68% of the observable universe's total mass energy content.
68%. That number just feels unreal. We spend all our time thinking about stars, planets, galaxies.
Like all of that, all those visible things, which we call ordinary baryonic matter, they account for a paltry 5%.
Just 5.
The remaining 27% is dark matter. That gravitational glue we still can't identify. So what we're dealing with here is a force, or an entity, that constitutes more than 2/3 of reality.
A force we only discovered, 25 years ago?
Exactly. And we label it dark purely because we have no idea what it is. It's the dominant mystery.
So our mission today is ambitious, but I think necessary. We've compiled a deep stack of sources spanning from the theoretical papers of the early 20th century all the way up to the latest data releases from global surveys. We are going to unpack not just what dark energy does, but critically, how we proved its existence through multiple independent measurements, why it's challenging our deepest theories of quantum physics, and, of course, what its presence means for the ultimate fate of everything.
And just to ground us right away, the observed function of dark energy is really twofold. First, and this is the big one, it is driving the accelerated expansion of the cosmos. And second, its presence creates this pervasive background pressure that actively slows the rate at which large cosmic structures, like galaxy clusters, can form and grow. It is essentially an anti-gravity engine built into the vacuum of space itself.
Okay, let's start where so many of these cosmological stories begin,
Right.
with Albert Einstein and what he famously considered his greatest blunder.
Right.
The concept of dark energy, or, something like it first entered physics through a kind of theoretical loophole.
That's exactly right. The concept of a constant energy inherent to space was introduced by Einstein way back in 1917, just after he finalized general relativity. He called it the cosmological constant, symbolized by the Greek letter lambda.
And he added it not because he observed anything accelerating, but because he was trying to solve a sort of philosophical problem about the universe's structure, correct?
Precisely. His general relativity equations, the ones that describe how mass and energy warp spacetime, they naturally predicted a dynamic universe.
So one that should either be collapsing from gravity or
expanding. But at the time, the prevailing philosophical view, which Einstein shared, was that the universe was stable, static, and eternal.
So he essentially used lambda as a break, a cosmic break.
Exactly. He shoehorned this constant into his gravitational field equations to mathematically force a solution for a static cosmos. It was meant to create a perfect counterbalance to gravity's attraction.
And how did he picture it?
He viewed this constant term as energy inherent to empty space vacuum energy that exerted a pressure equivalent to gravitating negative masses that are distributed all over the interstellar space.
Yeah.
So in concept, it was negative gravity balancing positive attractive gravity.
That sounds incredibly fragile. Was this static universe he predicted even stable?
No, and that's where the physics immediately got dicey. Even mathematically, his static model was found to be unstable. Imagine balancing a pencil on its sharpened tip. It's technically in equilibrium, but the slightest puff of air, the smallest perturbation, and it falls over. If the universe contracted just slightly, gravity would win and cause a runaway collapse. If it expanded slightly, that constant vacuum energy would be released, causing a runaway expansion.
And then the observational hammer blow came just 12 years later.
It did. Edwin Hubble's observations in 1929, based on measuring distant galaxies, provided the empirical proof that the universe was, in fact, expanding, not static at all.
And what did Einstein do?
When he learned of this, he reportedly abandoned lambda completely, calling its introduction his greatest blunder. He realized he had missed probably the most profound prediction of his own theory. a dynamic, evolving cosmos.
So the idea was just shelved for decades, except for one notable early exception, right? Cosmic inflation.
Yes, the precursor concept. Inflation is the theory that during the first tiny fraction of a second, like 10 to the minus 32 seconds after the Big Bang, a negative pressure field, conceptually very similar to lambda, drove this immense exponential expansion that smoothed out the entire universe.
So a repulsive energy drove the universe at its birth, just at a vastly, vastly higher scale.
That's the key distinction. Inflation required a field operating at an immensely higher energy density than the dark energy we see today, and it shut off almost instantly.
And after that?
After inflation, the universe was dominated by radiation and matter, and physicists just assumed the cosmological constant was zero, or at least negligible, for the rest of cosmic history.
Which takes us from the 1930s all the way to the 1990s. And the consensus leading into that decade was that the universe was slowing down, or at best, holding steady. What was the dominant model then?
Well, throughout the 80s and early 90s, cosmology really favored critical density models. The idea was that the total density had to equal 100% of the critical density to produce a geometrically flat universe,
Which inflation predicted.
which many inflation models predicted, yes. Since visible matter was clearly not enough, the missing mass was assumed to be cold dark matter, or CDM, and this total mass was expected to slow the expansion rate due to gravity. The primary expectation was deceleration.
So gravity should have been applying the brakes the whole time. What was the stunning observation that just flipped the script?
The key discovery came in 1998 from two independent international collaborations: the High-Z Supernova Search Team, led by Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter.
And they were using those distant type Ia supernovae as cosmic distance markers.
They were, and their shocking simultaneous finding was that the expansion was not slowing down.
It was accelerated.
It was accelerating.
It's just astonishing that a theoretical concept once deemed a mistake energy inherent to space was suddenly demanded by observation.
It was scientific history unfolding in real time. The need for some kind of smoothly distributed negative pressure component was immediate and undeniable. And it was in 1998 that the cosmologist Michael S. Turner coined the specific term dark energy to describe this mysterious component driving the late-time acceleration.
So the universe was found to be dominated by the very force Einstein had introduced and then rejected.
The ultimate redemption story for a theory.
Okay, let's unpack this physically. The observations tell us dark energy creates anti-gravity. How does a property of space itself manage to exert a repulsive force?
For that, we have to consult the blueprints of the universe, general relativity. In GR, gravity isn't just affected by mass and energy density.
Right, it's also affected by pressure.
Exactly. Pressure, symbolized by P. This is all captured in the stress energy tensor. For normal matter, like a gas or a star, the pressure is positive, and this positive pressure actually contributes to the overall gravitational attraction.
But dark energy doesn't have positive pressure. It has a strong negative pressure, a tension. And that's the crucial element, isn't it?
It is. Negative pressure means the substance is essentially under tension. In general relativity, this strong negative pressure exerts a repulsive gravitational effect. It is the only way to get accelerated expansion.
Can you give us an analogy?
Think of it like a rubber sheet being pulled taut everywhere. The fabric itself is trying to pull apart. The negative pressure causes the space-time metric to stretch, which is why cosmologists often refer to the effect as gravitational repulsion.
That still feels a bit counterintuitive. If it's under tension, why doesn't that tension pull things together?
The key is that this tension is inherent to the vacuum itself. Imagine a piston drawing a vacuum in a cylinder. The vacuum resists the increasing volume. It tries to pull the piston back.
Okay.
When the universe expands, dark energy resists that volume increase, which, in the framework of general relativity, translates into an energy density that drives the expansion even faster. It doesn't clump. It's extremely homogeneous, just uniformly filling otherwise empty space.
And the numbers confirm just how sparse it is. It's incredibly dilute.
Oh, very dilute. The density is measured to be around 10 to the minus 27 kilograms per cubic meter. I mean, if you tried to measure the mass energy of dark energy in your living room, it would be minuscule. It's about 7/60 of a gram per cubic centimeter, an incredibly low energy density.
So if it's so incredibly wet and dilute, how does it overcome the gravitational attraction of all the stars and galaxies in the universe?
This is where its unique dilution property comes into play, and this is maybe the single most important concept to grasp about dark energy.
Okay.
Matter density and radiation density dilute dramatically as the universe expands.
Let's break that down. Matter density drops inversely with the cube of the scale factor, right? So rho is proportional to the -3.
Correct. If the universe doubles its scale factor, doubles in size, the volume increases by 8 times. So the density of matter drops to 1/8 of its original value.
And radiation.
Radiation density, like light, drops even faster, proportional to the -4, because not only does the volume increase, but the light waves themselves are stretched by expansion, which decreases their energy. That's redshift.
So matter and radiation weaken their influence dramatically over time.
But dark energy is fundamentally different. If it's the cosmological constant, lambda, it is an intrinsic property of the vacuum, and its density remains stubbornly constant regardless of expansion.
Proportional to the zero.
Exactly. As space expands and the volume increases, more dark energy just appears to fill that new space, maintaining its low, fixed density.
That means in the early universe, attractive matter and radiation were extremely dense and easily dominated dark energy's constant but very low repulsive influence.
Precisely. For the first 9 billion years of cosmic history, gravity was winning. The expansion was decelerating. But because matter and radiation kept thinning out, there came a point where their density dropped below the constant density of dark energy.
And that's when the shift happened.
Yes. Cosmologists estimate this critical shift occurred roughly 5 billion years ago, which corresponds to a redshift of about z equals 0.4. That moment marked the end of the matter-dominated era and the beginning of the current accelerating dark energy-dominated era.
Which explains why the acceleration is a late-time phenomenon.
That's why we're only seeing it now.
Okay, so if the entire lambda CDM model rests on the existence of dark energy, we need some ironclad proof. And unfortunately, the argument for its reality doesn't just come from one source. It relies on 3 independent, massive pillars of evidence.
That's right.
Let's start with the famous one, supernovae as standard candles.
The standard candle method is basically a cosmic ruler. We rely on the type Ia supernova.
Which is when a white dwarf in a binary system just gets too heavy.
It exceeds the Chandrasekhar limit and undergoes a thermonuclear explosion. Crucially, because they always explode at roughly the same mass, their peak absolute luminosity is reliably constant. They are effectively calibrated light bulbs scattered across the cosmos.
So we know how bright they truly are, which is L, and we measure how bright they appear to us from Earth, F.
Exactly. Using the inverse square law of flux, we can determine the distance. We then compare this calculated distance to the galaxy's redshift, which tells us how quickly it's receding due to expansion. The expectation, based on a matter-dominated universe, was a specific relationship between distance and redshift.
But the 1998 discovery found that distant Type Ia supernovae were dimmer than expected for their measured redshift. What does dimmer than expected imply?
Well, if something is dimmer, it must be farther away. The distant supernovae were farther away than they should have been if the expansion rate had been constant or slowing down due to gravity. This implies that since they exploded, the space between them and us has expanded more rapidly than expected. It's the direct observational fingerprint of acceleration.
And this still holds up.
Absolutely. Recent studies, like those published in 2022, consistently confirm that about 66.6% of the energy density is dark energy, assuming the flat lambda CDM model.
Okay, the second massive piece of evidence takes us way back to the ultra-early universe, the cosmic microwave background, or CMB. This tells us about the geometry of space.
Correct. The CMB is the afterglow of the Big Bang, a snapshot of the universe when it was only about 380,000 years old. Detailed measurements of the temperature anisotropies, those tiny hot and cold spots, allow cosmologists to determine the overall geometry of the universe.
And the results.
These measurements, first pioneered by WMAP and later refined by the Planck satellite, overwhelmingly indicate the universe is geometrically very close to flat.
Help us visualize flat. What does a flat universe mean compared to, say, a curved one?
Imagine a massive triangle drawn across the cosmos. In a positively curved or closed universe like the surface of a sphere, the internal angles of that triangle would add up to more than 180 degrees.
Right.
In a negatively curved or open universe like the surface of a saddle, they would add up to less than 180. In a flat universe, space follows Euclidean geometry. Parallel lines remain parallel, angles add up to exactly 180 degrees, and the CMB data confirms this flatness.
So, if the universe is flat, what must be true of its total contents?
General relativity demands that for space to be flat, the total mass energy density must be precisely equal to the critical density. 100%.
But when we add up the stuff we can measure,
When we add up the measurable constituents ordinary matter and dark matter based on the CMB spectrum, we find they only account for about 30% of that critical density,
this leaves a massive deficit.
a 70% deficit, which must be accounted for by the missing component that doesn't clump gravitationally, but provides the necessary energy density to make the universe flat. That component has to be dark energy.
And the numbers line up.
Perfectly. Data from the Planck mission in 2013, for instance, gave the value of 68.3% for dark energy, aligning almost perfectly with what's required for flatness.
Okay, our third piece of evidence moves from the ultra-early universe to the large-scale structure of the cosmos today, using galaxy surveys.
This is the large-scale structure, or LSS, evidence. The way galaxies and galaxy clusters are distributed across billions of light years confirms that the total amount of matter, both baryonic and dark, is insufficient to drive the cosmos.
Again, around that 30% number.
Around 30%, yes. But LSS offers a crucial independent measurement tool, baryon acoustic oscillations, or BAOs.
These are often referred to as standard rulers. How are they formed, and how do we use them?
In the hot, dense, early universe, pressure waves, sound waves traveled through the plasma, pushing ordinary matter and dark matter out. When the universe cooled and became transparent at the time of the CMB, these waves froze,
Leaving an imprint.
leaving a characteristic spatial scale, an overdensity of galaxies separated by a distance of approximately 150 megaparsecs. This fixed distance is our standard ruler.
So by measuring the apparent angular size of this standard ruler in distant galaxies, we can infer their distance. It's like knowing a yardstick is exactly a yard long and then measuring its apparent length from far away.
Exactly. The Wiggle-Z Galaxy Survey, which released data in 2011, measured these BAOs out to 2,000 megaparsecs. That's over 7 billion light years. And critically, this data independently verified cosmic acceleration stretching back 7 billion years.
So it confirmed the conclusions from the supernovae and the CMB flatness data.
A three-pronged attack, all pointing to the same answer.
And finally, let's just touch on the more advanced technique that is considered a direct signal of dark energy operating on gravitational potential. The late-time integrated Sachs-Wolf effect, the ISW effect.
Right. The ISW effect is a change in energy experienced by CMB photons as they travel through gravitational potential wells and hills created by massive structures like superclusters and supervoids.
Okay, what does that mean in practice?
In a universe without dark energy, the expansion rate would be constant or slowing. This means a photon would lose the same amount of energy climbing out of a potential well as it gained falling in. So, a net zero energy change.
But accelerated expansion changes the rules.
It does. Because dark energy is causing the universe to accelerate, the gravitational potential wells actually flatten out while the photon is passing through them. The depth of the well diminishes between when the photon enters and when it leaves.
So the photon gains more energy falling in than it loses climbing out.
The net result is a slight increase in the photon's energy, a blue shift. Detecting this requires correlating the locations of superclusters and supervoids with subtle temperature variations in the CMB. And its high significance detection is considered direct evidence of cosmic acceleration.
And it only works in a flat universe dominated by dark energy.
That's right, it's another powerful confirmation.
The observations are solid, but the scientific core remains. What physically is dark energy? The simplest candidate is the one that's currently the default. Einstein's original idea, the cosmological constant, lambda.
The cosmological constant is fundamental vacuum energy intrinsic to space itself. This model is preferred because it's the simplest mathematical fix that fits all the major observations to high precision. It's the bedrock of the lambda CDM model.
But this is where we run directly into what has been called the single worst theoretical prediction in the history of science, the cosmological constant problem.
This is a profound conceptual conflict between general relativity and quantum field theory. QFT predicts that even empty space is teeming with virtual particles, constantly popping in and out of existence.
And these contribute energy.
Each of these virtual processes contributes energy to the vacuum. When quantum physicists calculate the expected total vacuum energy density, the theoretical value for lambda, they get a number that is just mind-bogglingly large.
How large is this predicted value compared to the actual observed value?
It is about 120 orders of magnitude too large.
10 to the power of 120.
Yes. To put that catastrophic difference into perspective, 10 to the 120 is the ratio of the mass of the entire observable universe to the mass of a single proton. That's the scale of the disagreement.
That's not just wrong, it's spectacularly wrong.
It's so wrong. It's almost certainly pointing to something fundamental we're missing. If the universe had the dark energy density predicted by QFT, it would have ripped itself apart the instant after the Big Bang. No atoms, no stars, no galaxies could have ever formed.
So if we accept the observed value, it means the enormous vacuum energy predicted by quantum theory must be canceled out by an equally massive but negative term, some mysterious anti-energy, with an astonishing precision of 1 part in 10 to the 120.
It's the fine-tuning problem from hell. This virtually perfect cancellation, for which we have no theoretical explanation, is why many physicists find the cosmological constant model theoretically unsatisfying, even though it works observationally.
It suggests physics at the most fundamental level is broken, or that we are just incredibly, unbelievably lucky.
Which is why we have to explore quintessence, the dynamic alternative.
Quintessence, it sounds appropriately ethereal.
It posits that dark energy is the potential energy of a dynamic scalar field. Unlike the constant lambda, this quintessence field has its own dynamics and can vary in space and time.
And it must have some very specific properties,
It
right?
must be extremely light, with a very large Compton wavelength, to avoid clumping and forming structures like matter does.
So it's more like a subtle fluid that pervades everything, rather than a fixed property of space. And this dynamic nature is what allows it to tackle another major mystery, the coincidence problem.
Ah, the coincidence problem. This asks, why did dark energy begin dominating so recently? Given the age of the universe is about 13.8 billion years, the acceleration shift 5 billion years ago seems awkwardly timed, just as complex life was forming on Earth.
If lambda is a constant, this timing is a pure statistical accident.
It is. But quintessence can offer a solution through so-called tracker models.
Tracker models.
These models are engineered so that the quintessence field density naturally tracks or follows the dominant density component, first radiation, then matter, but always remains a slightly smaller fraction of the total energy.
Okay, so it's always lurking in the background.
Exactly. But critically, when the universe reaches matter-radiation equality, the field activates, and its density curve shifts, naturally triggering its dominance at a later, low-energy scale. This provides a physical explanation for the timing, eliminating the need for cosmic luck.
Are there more extreme or speculative versions of this dynamic field?
Absolutely. We have models that push the boundaries of what dark energy can do. For instance, phantom dark energy is a speculative case where the energy density actually increases over time.
Which leads to the Big Rip scenario we'll discuss later.
It does. There are also quantum models, which propose the existence of at least 2 scalar fields to explain certain observational subtleties.
And speaking of evolution, the newest research focuses on whether dark energy density is changing at all. This is the realm of variable dark energy models.
This is a really hot area right now because even a tiny measurable change over cosmic time would immediately invalidate the constant cosmological constant and force us toward a dynamic model like quintessence.
We have some fresh data on this, don't we? From the Dark Energy Spectroscopic Instrument Collaboration, DESI.
We do. The DSI collaboration, in March 2025, announced preliminary observational evidence suggesting that the density of dark energy is slowly decreasing over time. They analyzed baryon acoustic oscillation data, combining it with CMB and supernovae measurements.
What specifically did the DSI analysis suggest?
Their findings indicated that the energy density of dark energy might have been about 10% lower 4.5 billion years ago compared to its current value. The statistical significance of this was between 2.8 and 4.2 sigma.
Okay, in particle physics, 5 sigma is the gold standard for discovery. So 4.2 sigma is extremely compelling, but it's not definitive.
Exactly. It's a provocative finding that currently cannot definitively rule out the simple constant lambda model, but it puts immense pressure on it. It provides the strongest observational motivation yet for new physics.
For a universe where dark energy is not fixed but is slowly evolving, perhaps fading in strength over billions of years.
There's a tantalizing clue.
This brings us to the conceptual hurdle that stops most people cold. How can the universe be expanding faster than the speed of light without fundamentally breaking Einstein's laws of physics?
It is a phenomenal point, and it requires us to be extremely precise about what special relativity actually says. The core principle holds true. Nothing with mass can travel through space faster than the speed of light, c in the local reference frame.
Right. If I fire a laser past you, the light still travels at c.
Always.
So if the law holds locally, What is happening globally that allows for superluminal speeds?
The crucial distinction is that the expansion of the universe is not the motion of objects through space. It is the stretching of space itself. General relativity allows the space-time metric, the fabric defining distance, to stretch or contract arbitrarily fast because space itself has no mass. It's not constrained by the local speed limit of c.
I often use the analogy of the inflating balloon with dots drawn on it representing galaxies. The dots aren't physically crawling across the rubber faster than c, the rubber itself between them is stretching.
That analogy is excellent for illustrating the mechanism. The stretching is codified by Hubble's law. Recession velocity is proportional to distance. V equals h times d.
So the farther apart two objects are,
The more space is stretching between them, and the faster their apparent recession speed. So if the distance is vast enough, billions of light years, the aggregate stretching of all that space between us and a distant galaxy can easily result in an apparent recession velocity that exceeds c.
so if a galaxy is far enough away, the rate at which new space is being created between us is so rapid that any light that galaxy emits toward us will get pulled backward faster than it can travel forward.
And that light will never reach us. This defines the cosmological event horizon.
Let me challenge that balloon analogy, though, because this is what often confuses listeners. If space is stretching, why aren't the things in space stretching? Why don't hydrogen atoms or planets or even the Milky Way expand?
That is where the analogy breaks down, and where the subtle distinction in cosmology becomes crucial. Dark energy is incredibly dilute, remember. Its density is 10 to the minus 27 kilograms per cubic meter. The forces holding local structures together, gravity, electromagnetism, the strong nuclear force, are vastly, vastly stronger than the repulsive pull of dark energy.
So the local gravitational pull within a galaxy easily overwhelms the minute expansion force of the surrounding dark energy.
Exactly. The local gravitational effects dominate completely inside bound structures. The expansion is only noticeable when you look at vast, unbound distances between galaxy clusters.
Now, I know some prominent cosmologists have objected to the expanding space language entirely, calling it misleading. Figures like Martin Rees and Steven Weinberg suggest we should just think of distant galaxies rushing apart. Why the opposition?
They argue that talking about stretching space anthropomorphizes the metric and leads to confusion over local versus global effects. If you just view it as objects moving away from each other, it can feel more Newtonian.
But that Newtonian view quickly leads to the incorrect conclusion that objects can move faster than light, violating the local rule.
It does. The stretching metric idea, while conceptually difficult, is mathematically necessary to explain things like cosmological redshift. The light wave itself gets stretched along with the fabric of space, causing its wavelength to increase and its energy to drop.
So it's a necessary conceptual aid.
It is. Ultimately, the rule that objects cannot pass by each other faster than km holds locally, but the global recession velocity, driven by the stretching of space, is not bound by that limit. It is a feature of the universe, not a broken law of physics.
Okay, the evidence for accelerated expansion is strong, but the acceptance of a 68% mysterious energy component is a high bar. What are the major competing theories trying to explain the observations without invoking dark energy? This is the skeptic's corner.
The first major category of alternative theories involves questioning the fundamental law of gravity itself, modified gravity.
If dark energy is essentially a term Einstein added to general relativity, why not just change general relativity entirely?
That's the idea. Modified gravity theories propose that general relativity may need modification on the largest cosmic scales to explain why gravity appears repulsive at vast distances. The most famous modifications, often called F of R theories, introduce new terms into the gravitational field equations.
And the hope is that these terms mimic the effects of dark energy.
Exactly, without requiring a new component of the universe.
But hasn't a major 2017 observation severely constrained or ruled out many of these models?
Yes, the observation of the gravitational wave event, GW170817, the merger of two neutron stars, was monumental. For the first time, we measured a gravitational wave signal alongside its corresponding electromagnetic signal.
We saw it and we felt it at the same time.
And this proved, with incredible precision, that the speed of gravity is the same as the speed of light. Many modified gravity models predict a difference in these speeds on cosmological scales, and those models are now essentially ruled out.
That's a huge victory for standard general relativity, even if it forces us to accept the mystery of dark energy. What about theories that suggest we are fundamentally misinterpreting the expansion because of our location? This is observational skepticism.
This is the realm of inhomogeneous cosmology. The standard cosmological principle assumes the universe is homogeneous and isotropic uniform everywhere on the largest scales. But if that assumption is flawed,
Say if we're in an unusually empty spot.
exactly, if we're located in an emptier than average region, a Hubble bubble, the observed expansion could be misinterpreted. If the space around us is less dense than the average density of the distant universe, light from those denser regions might appear redshifted and dimmer in a way that mimics acceleration,
But these models face enormous challenges, right?
primarily from the uniformity of the CMB, which strongly suggests that the early universe was extremely homogeneous. Most efforts to successfully debunk dark energy observations have been pretty quickly rebutted by the cosmological community.
Okay, now let's look at the newest and maybe most compelling alternative that links two cosmic mysteries. The 2023 proposal that black holes are the source of dark energy through cosmological coupling.
This is a radical concept because it suggests we might not need a new field at all. The theory proposes that black holes are not static in general relativity, but are cosmologically coupled to the expansion of the universe, which leads them to gain mass over time.
A growing black hole, how does that mimic the constant density of dark energy?
The critical calculation shows that the rate of mass gain for a black hole must be proportional to the cube of the cosmic scale factor, a cubed. Since volume also increases proportional to a cubed, the calculation means that the collective energy density of all black holes in the universe remains perfectly constant over time.
So the aggregate energy density of growing black holes behaves precisely like the cosmological constant.
Exactly. This would mean that the 68% energy budget we attribute to dark energy is actually accounted for by the constant energy density of vast cosmologically coupled black holes. It's a powerful, elegant connection.
Is it widely accepted?
No, the idea faces intense astrophysical scrutiny. Many scientists are highly skeptical about the required magnitude of the mass gain, but it represents a really active area of research.
And finally, a highly theoretical, non-mainstream alternative. Shockwave cosmology.
This concept, pioneered by Smaller and Temple, suggests that the Big Bang was not a uniform event, but an explosion that occurred inside a black hole.
Wow.
A related model proposes that the observed acceleration is not due to a pervasive energy, but is simply the effect of us living in a region with a lower density than the surrounding space, an inhomogeneity created by the initial shock wave propagating outward.
So acceleration is a result of the universe's structure, not a vacuum force. And this model has a specific testable prediction that differs from lambda CDM.
Yes, and this is the vital part for science. The standard lambda CDM model predicts a specific small cubic correction term to the redshift versus luminosity relationship for supernovae, which is C is approximately minus 0.180.
And the shockwave model.
It predicts a distinctly different value. C equals positive 0.359. These are significantly different numbers, meaning that future high-precision measurements of distant supernovae will either validate the standard model or potentially confirm this radical alternative. The race is on to measure that correction factor with enough certainty.
Whether we believe dark energy is a constant, a dynamic field, or perhaps even an illusion, our current standard model, lambda CDM, is currently under immense theoretical and observational strain. This crisis is known as the Hubble tension.
The Hubble tension is arguably the biggest crisis in modern cosmology, and it reveals a deep flaw in our current understanding of the universe's evolution.
What is it exactly?
The Hubble constant, h0, quantifies the present-day expansion rate. The tension is the irreconcilable discrepancy between two methods of measuring this constant.
Let's lay out the conflicting numbers and methods.
We have two families of measurements. First, the early universe prediction. This uses the standard lambda CDM model, calibrated with data from the early universe, specifically the physics derived from the cosmic microwave background and baryon acoustic oscillations.
And that gives us a number.
These predictive models consistently calculate h not to be around 67 to 68 kilometers per second per megaparsec.
This is the prediction of the standard model. But what do we see when we look locally right now?
The second family is the local universe observation. These are direct, present-day measurements using standard candles like Type A supernovae and geometric distance ladders in nearby galaxies. These methods consistently yield higher values, averaging closer to 73 kilometers per second per megaparsec.
That 5 to 6 difference is enormous in cosmology. For years, scientists hoped it was just a measurement error in the local data, maybe a flaw in the Hubble Space Telescope calibration.
That hope has been largely extinguished. New high-resolution observations from the James Webb Space Telescope, published in late 2024, used the largest sample of distance markers yet to confirm the local measurements.
So JWST confirmed Hubble's numbers.
It did. The JWST's findings ruled out a significant systematic error in the local distance ladder methods. The data is robust. The theory is where the problem lies.
So the Hubble tension is not a data problem, but a crisis of theory. The standard model, which works beautifully everywhere else, cannot predict the current expansion rate accurately. This implies missing physics.
It implies that the universe expanded slightly faster in its infancy than the lambda CDM model predicts. The tension is forcing theorists to propose radical fixes new physics that must exist between the time of the Big Bang and the era of the CMB formation.
What specific theoretical patches have been proposed to bridge this gap?
The leading candidate solution is early dark energy, or EDE. This posits a brief burst of dark energy-like activity shortly after the Big Bang.
How would an early burst solve the current tension?
EDE would momentarily dominate the energy budget and give the universe an unexpected kick, increasing its expansion rate just slightly in the early stages. This would alter the size of the sound horizon, the physical scale of the BAOs visible in the CMB.
And that fixes the numbers.
By increasing the early expansion rate, the EDE model can reconcile the lower CMB prediction with the higher local observation, without disrupting the late-time acceleration caused by dark energy today.
Are there other exotic particles or properties that might be missing from our early universe models?
Yes, theorists have explored funny dark matter properties, changes in fundamental constants, or exotic particles like sterile neutrinos.
What are those?
Sterile neutrinos are purely theoretical, non-interacting particles. If they existed and contributed to the energy density of the early universe as a form of dark radiation, they would similarly increase the expansion rate just enough to potentially relieve the tension.
The very existence of this tension confirms that we are entering a golden age of cosmology, driven by the realization that our standard model is incomplete, and we are now throwing massive hardware at this problem.
That's the exciting part. We have entered the era of precision cosmology, and massive global missions are underway or launching soon, explicitly designed to map dark energy and resolve the Hubble mystery.
Let's survey the technology we're deploying.
First, we have ESA's Euclid mission, launched in 2023. Euclid is creating a monumental 3D map of the universe, covering 1/3 of the sky. By observing billions of galaxies, it traces how dark energy has influenced the distribution of matter over cosmic time.
And NASA's flagship effort, the Nancy Grace Roman Space Telescope.
Roman, set to launch by May 2027, is a true game-changer. It combines the resolution of Hubble with a field of view 100 times larger. It's specifically designed to address the dark energy mystery by conducting massive surveys of weak gravitational lensing and Tripaya supernovae.
And the ground-based contributions.
We have the Vera C. Rubin Observatory in Chile, expected to become operational in 2025. It'll conduct the legacy survey of space and time, generating petabytes of imaging data that will be crucial for mapping the underlying dark matter distribution.
And the near-infrared survey, SphereX.
NASA's SphereX mission, launching by April 2025, will conduct the first all-sky spectroscopic survey in near-infrared light. It expects to observe over 450 million galaxies and use their spectra to precisely map the three-dimensional distribution of cosmic structures.
So, more BAO measurements.
An independent set of BAO measurements to refine the dark energy equation of state and help resolve the Hubble tension. These missions, working in concert, should theoretically be able to move dark energy from a placeholder hypothesis to a verified physical field.
And, we hope, force the solution to the Hubble tension. The nature of dark energy is the key to our cosmic fate. If this repulsive force remains dominant, what do the models project for the ultimate end of existence?
Well, the universe's fate depends entirely on the dark energy equation of state, whether its density remains constant or changes. The most likely scenario, supported by the simplest model, is indefinite acceleration, leading to heat death or the big freeze.
That's the scenario where the universe asymptotically approaches thermodynamic equilibrium.
Exactly. If dark energy remains constant, the universe continues to expand and cool, constantly increasing its entropy. Eventually, all matter and energy will be so uniformly distributed that no further thermodynamic work will be possible.
No temperature gradients, no usable energy.
Just a dark, cold, diffuse soup of fundamental particles.
What are the astronomical consequences of this indefinite acceleration for us in the local group?
The vast majority of the universe will eventually recede faster than the speed of light. This means all galaxies outside our local group, that's the Milky Way, Andromeda, and their satellites, will cross a cosmological event horizon, currently about 16 billion light years distant.
And what does that cosmological event horizon imply for light?
Permanent isolation. Once a light source crosses that horizon, any light it emits after that point will never, ever be able to reach us. The expansion of space will simply carry it away faster than it can travel toward us.
So future astronomers.
Future astronomers, maybe 10 to the 12 years from now, will look out and see a vast, empty void. Our local group will be a tiny, lonely island of stars in complete darkness, forever unaware of the 99.9% of the universe that vanished over the horizon.
That paints a haunting philosophical picture. And what happens on the unfathomably long timescales when the stars themselves have died?
The stellar era will end within about 10 to the 14 years. The remnants, white dwarfs, neutron stars, black holes will slowly decay. Even the largest supermassive black holes will evaporate completely via Hawking radiation.
And that takes how long?
An astonishingly long time, up to 10 to the 106 years. The universe then enters the dark era, composed primarily of diffuse photons, neutrinos, and leptons, approaching the thermodynamic zero of the Big Chill.
A quiet, slow fade. But there is a much more violent, catastrophic alternative. The Big Rip.
The Big Rip is the consequence of the speculative phantom dark energy model, where the energy density of dark energy actually increases over time.
So the repulsive force grows stronger. What is its ultimate fate?
The force becomes so overwhelming that it begins to dominate all other fundamental forces. First, it tears apart gravitationally bound structures, galaxy clusters, galaxy solar systems. Then, on much shorter timescales, it overcomes electromagnetic forces, tearing apart planets, rocks, and molecules.
And finally, it overcomes the nuclear forces, tearing apart atoms themselves.
Correct. In the final fraction of a second, the increasing phantom energy density becomes infinite, ripping apart nuclei and fundamental particles. It represents a cataclysmic, explosive end to space and time itself.
Are there any theoretical scenarios where the universe reverses course, where gravity reasserts dominance?
These are highly speculative, but necessary to consider. If dark energy somehow dissipates, decays, or changes its sign becoming attractive rather than repulsive gravity could eventually prevail, leading to the big crunch.
A contraction back into a singularity.
Or other models propose a cyclic model, where the changing nature of dark energy leads to an endless series of big bangs and big crunches, potentially repeating every trillion years or so. These models attempt to avoid the finality of the heat death, or the Big Rip.
Finally, we should acknowledge the philosophical weight of adding dark energy in the first place. David Merritt frames dark energy not as a discovery, but as an auxiliary hypothesis, a term added to general relativity, because the original theory was observationally falsified by the discovery of acceleration.
That perspective is a powerful critique of modern cosmology. It suggests that dark energy is currently just a necessary placeholder to balance the equation until we discover the true underlying physics. Until we can understand what it is physically, it remains a massive 68% question mark in the universe's budget.
A question mark forced upon us by the observations.
Exactly.
This deep dive took us on a century-spanning journey, from Einstein's famous blunder to the Nobel-winning discovery of cosmic acceleration. We followed two great threads: the strange nature of dark energy as the universe's dominant negative pressure anti-gravity, and the critical observational challenge posed by the Hubble tension, which suggests our textbook knowledge of the early universe is fundamentally incomplete.
The core knowledge you gain today is crucial. You now understand why the universe can expand faster than the speed of light. It's the stretching of the space-time metric, not objects violating local speed limits. And you know that the idea of dark energy originated from using type Ia supernovae as extraordinarily precise cosmic distance rulers.
Which proved distant objects were far dimmer and therefore much farther away than expected for a decelerating cosmos. We also noted that the universe began accelerating about 5 billion years ago, which is remarkably recent in cosmic terms. If the lambda CDM model is correct, that constant dark energy density was always there, just waiting for matter to dilute enough so that its persistent low pressure could take over.
Which brings us back to that fundamental philosophical puzzle we raised earlier, the coincidence problem. Why did this shift happen precisely when there was just enough time for stars, planets, and observers like us to evolve?
If the timing was purely accidental, a cosmic coincidence, it means our entire existence is a massive statistical fluke, occurring in the narrow window before the cosmic event horizon closes in, locking us off from the universe forever.
But if the timing was tied to some natural mechanism like the dynamic tracker models of quintessence, which naturally delayed dominance until matter density dropped, does that suggest a deeper underlying physical clockwork is at work, perhaps even related to the mechanism that formed matter itself?
That ultimately is the question that sits at the center of modern physics. It means the biggest question might not just be what dark energy is, but whether its timing suggests our existence is a cosmic accident or a consequence of a deep, coordinated mechanism.
It's the ultimate question.
Thank you for joining us for the deep dive. We'll see you next time.